Kliegl to the lab meeting of the TeDCog group, and he's one of our luminaries, our external speakers, who used to be at the University of Potsdam for many years, and who's now moved on to bigger and better things in St. Petersburg. And yeah, I really look forward to what you have to say. Over to you, Reinhold.
Well, thank you, Steve. This is really quite exciting for me. It's the first time I'm using this new affiliation. I still also have an affiliation with Potsdam, by the way, but this is the project that that is clearly owed to St. Petersburg, and I start right away. Okay, so basically, when we do experiments, web experiments, where we ask people to discriminate fake and true news, there are traditionally two approaches people take. One is that they, in a way, ask people, do you trust that news, which is really, like a credibility rating. So you ask people, give it a rating. How is this sort of definitely true, or is it definitely not true? And that's 1 would be definitely fake, and 6 would be definitely true. And 3 is sort of a little bit more towards the no side, and 4 is a little bit more towards the yes side. And the alternative is, of course, that we can measure the accuracy, how good people are in recognizing and discriminating the true and the fake news. And so I came across that big study that had already been carried out. And there are actually 2 papers that exemplify these 2 approaches. One is that paper by Kirill Bryanov, and I'm already part of that one, where we basically did an analysis of the ratings, of the credibility ratings, as a function of a whole bunch of stuff. I'll talk a little bit more about that later. And at the same time, there's also a chapter that's published by Alexander Porshnev, also from the same group, where they basically focused on the accuracy of discriminating those kinds of things. Now, for me, that whole fake news business and web experiments is really something very new. I'd never done that before, but actually Steve has been my tutor for the last 3 years, and actually he allowed me once to give his presentation at the Berlin Academy, which I thought was really very generous of you, Steve, because I didn't have any data myself, but I definitely wanted to get into that field. And so this group here welcomed me very much. And so usually you thank the people at the end of the presentation, but I want to sort of reverse that and tell you just who is involved in that group at the outset. And then I don't forget to mention the people at the end. So that's the other reason. And so basically I'm affiliated with the Social and Cognitive Informatics Laboratory. And this laboratory is headed by Olesya Koltsova, and she's here. Olesya, maybe you just want to quickly wave. And yeah, she's by training a sociologist. And another person who was basically the lead author on the credibility rating paper is Kirill Bryanov. I haven't seen him, but he's worked in the United States and is very knowledgeable in political science and did work already in that area. Then Sergei Pashakhin is also a sociologist. He's here actually. Alexander Porshnev is a psychologist actually. He's also around. Jadwiga Sinyavskaya is a social network experiment. Maxim Tepilovsky is a biostatistician doing web experiments. And Victoria Vizyatisheva is a journalist student and media communication expert. And then this perk, I mean, you already saw that it's a project that involved really web users in Russia, in Kazakhstan, and in the Ukraine. And so there were also people from the Ukraine, and at least who originally are from the Ukraine or originally are from Kazakhstan, were also involved, Tetiana Lokot and Alexander Miltsov. And then sort of when I came there, and what I'm going to talk about today is really how can we analyze these 2 aspects of ratings, credibility ratings, and accuracy of discriminating fake and true news with a signal detection approach. And I sort of brought my friend Maximilian Rabe along. He is also around here. And so the people who are now basically listed in black on this slide are the ones that I'm currently working on implementing the signal detection approach as an R package. And what I'm going to show you today is basically a reanalysis of some of the data that we published in the Brianov et al. Paper, or not published, that is currently under review. We're actually currently revising it. And we can sort of directly compare a little with what the signal detection approach basically gives us beyond that. So now I assume that most of you are psychologists, and so you probably all have heard about signal detection theory before. I will not get too technical about it. And of course, my Russian friends, even if they are not in psychology, they already now have been hit over the head many times with this kind of stuff. So for them, a lot of that stuff is, of course, already very familiar. But it's very important. And I, of course, when it's the first time I give a talk about that, about signal detection theory in this context. And so it's, of course, important. How do you do that didactically, right? And I think it's really important to start with the theory. And because in a way, for those of you who have never thought about it from that perspective, it's a little bit of a shift in your mental model that you need to implement to really appreciate it, I would say. And the theory is really quite simple. It's not difficult. Conceptually, that's a nice thing. I always like theories that are conceptually simple. And this is really a conceptually simple theory. The theory basically says that when I read a piece of news, then if I read a piece of news that's true, if I read a piece of true news, then that will give rise to subjective evidence that this is a true piece of news. And that's basically on the x-axis here. And, if I look at many true news, the subjective evidence that accumulates in myself on my past knowledge will be normally distributed. So typically, there's a typical fake news, true news, that basically that would be the mean subjective evidence I have for true news. That's the one thing. So we assume there's a normal distribution of subjective evidence that the news are true if the news are true. And the same thing also, of course, now applies to the fake news. Now, obviously, fake news on average should not give me so much evidence that they are true. So the subjective evidence I get from fake news will be somewhat to the left of the subjective evidence that I get for the true news. And again, signal detection theory makes the assumption that these two distributions are normally distributed and they have equal variance. And basically now we have, and basically my ability to distinguish between the true and the fake news is the difference between the two means, and that's called the D prime. And I will refer to that as the discriminability. How discriminable are in principle, in theory, are the true and the fake news, given the distribution of subjective evidence I have for both of them. And that's really the parameter that psychophysicists were primarily interested in estimating all the time. They always wanted to know what is really the sensitivity of the person in discriminating, in this earlier times, a signal from noise, let's say. And we are discriminating fake news from true news, or true news from fake news. Now there's a second component, and the second component, and that's a well-known phenomenon in psychology, and especially actually also if you do fake news research, is that people will have a bias or will have a tendency to say yes or no to different degrees. And basically, when I'm going to judge whether a piece of news is true or not, in the signal detection theory, the assumption is made that there is a point on the x-axis here, and that's sort of the point that's demarcated by that vertical line, and it has a C, and that stands for criterion. And basically, whenever my subjective evidence is larger than that crossing point on the x-axis, then signal detection theory says, you say yes, I believe that is a true news. And whenever the subjective evidence isn't there, you say no. Okay, that's all there is. Now, if we have that criterion, what that means is now that basically, and let's now just assume that the area, that these are sort of standard normal distributions. So the area under the curve is 1. Okay. Now, basically, what I get now is an estimate of the hit rate and the false alarm rate. And the hit rate is basically the green hashed area. It's basically everything that's under the true news distribution to the right of the criterion. And I can express that area as a percentage of 1. Okay, so basically it's the probability of a hit rate. It's the probability of a hit rate. It's the probability of a correct response given that I had to charge a true news. And likewise, the area underneath the fake news distribution to the right of that criterion, which is sort of hashed in red, those are the false alarms. I say yes, although for a certain portion of news, they will come actually from the fake news distribution. All right, so we have the hit rate and the false alarm rate. And now basically, that's really at a descriptive level all we need to compute actually the location of the criterion and the D prime. So is everybody cool on that? Yeah, good. So why do we want to use that? Okay, signal detection is, I already said the upper stuff, okay? Now, of course, people can differ where they put that criterion. And so basically, when we shift the criterion around, we will change the proportion of hit rates and false alarm rates, right? And so that has always been the trick in signal detection theory, to basically get multiple estimates of those hit rates and false alarm rates by inducing people to shift their criterion. Now, the traditional ways of doing that is basically you increase the cost of a false alarm, of a false response, then people will more likely, of a false, I'm sorry, let me just stay here. And so the confidence ratings now in a way are to induce a shift of that criterion C. And let me just show that here basically on the next slide. Oops, I go here. So this is in a way the figure that I showed you before, right? And now the idea is that when a subject gives you a rating of 6, they are very sure that is a true news, right? Because you're definitely on the true side. And that means if your criterion is far to the right here, then that hit rate and the false alarm rate will be very small, right? But the hit rate will be bigger than the false alarm rate. So the area under the blue curve is still larger than the area under the black curve. But the hit rate will be larger than the false alarm rate. Now, when I give a rating of 5, the criterion is sort of shifted over here, and you sort of see I increase now. I'm now a little bit earlier. I say yes a little bit earlier with a little bit less of evidence. I'm already saying yes. And so that increases the hit rate, but it also increases the false alarm rate. And so we go and we just shift the criterion around. And so now basically when we use these kinds of a rating manipulation to estimate the D prime and the C's, we can basically evaluate these various proportions of hit rates and false alarm rates to allow us to get a good estimate of basically where are the distributions located. So in a way, we have to find the location, the hypothetical location of these two distributions in our mind in order to best accommodate the various hit rates and false alarm rates that we observe given the specific responses that subjects made. And that is really pretty much all there is to it. So if we have that, I give you now a little bit of the framework of how we are going to do that. Well, one more thing here. I'm sorry. The point is now basically that this distribution or this mental model will be different for different people. Different people will have their criterion somewhere else. Different people will have the distributions further apart or closer together. They will have different D primes. So we will have individual differences both in the D prime and in the location of the criterion. How likely am I going to say yes, given already a little bit of evidence? And at the same time now, if we have an experimental manipulation, the experimental manipulation will also shift this stuff around, right? And so basically we can now actually provide statistical tests of how much does the D prime change in response to a certain experimental manipulation, and how does the criterion change in a specific type of experimental manipulation. And with this background, basically, let's look at the space of variables that we have. Okay, so we basically start out with a credibility rating, and the rating is 1 is definitely fake news and 6 is definitely true news. From that, we can compute the hit rate, which is the % correct responses given that the subject was rating a true news item. And we can compute the fake false alarm rate, which is the % of incorrect values given that it was a fake news item. Okay, so they say yes, although they should have said no. And so 1 minus % correct given fake news would be the correct rejection rate, right? So all we need are the hit rate and the false alarm rate. And now comes the real beauty of that all. This is just absolutely gigantic. The D prime, if my model is correct, okay, now everything of course rests on the truth of my assumption of the signal detection theory. If I have these normally distributed pieces of subjective evidence, and if they have the same variance, then basically the D prime, that is the difference between the two distributions, is simply the difference between the C value for the hit rate and the C value for the false alarm rate. And the criterion, and that is simply actually the average of these two. And I insert that here because this is a highly underappreciated statistical fact. If you have two variables that are correlated and you C transform both of those variables, then the difference and the average correspond to the two principal components. So if you were to take your two variables and just jazz them into a principal component analysis, what you get out is two new indicators that are uncorrelated, because principal components are uncorrelated. So that means at the level of the signal detection theory, so I start out with the hit rate and the false alarm rate, but when I'm down at the D prime and the C at the criterion, I now have two uncorrelated indicators. Now that's really cool. That means at the lowest level, these two indicators, the sensitivity, the discriminability, and the bias are uncorrelated, right? So that's really important, and that also applies to a lot of other stuff. I actually did it by accident in my dissertation and found, and yeah, I forget it. Anyway, so now, okay, so this is basically, this is our measurement space that we are working with. Now, we are doing an experiment, and my Petersburg friends did a fantastic experiment. They manipulated, they not only had people read true and fake news, they actually manipulated the type of news depending on whether the news was written from the dominant perspective, let's say for simply that it was sort of in agreement with the mainstream, or whether the news was written more from an opponent's perspective, from the opposition perspective. And that's called the alternative narrative. So a news can represent a dominant narrative, or it can represent an alternative narrative. And that applied, that was crossed with the truth. So we have both true, dominant, and alternative, and we have fake, true, and alternative news. And they also, I just highlight a few things that I'm going to use. So there's a whole bunch of other stuff here, but basically, they also asked the users, how much do you support your government? Right? And we, of course, also had the information about age and sex. And there's another critical variable, which I'm going to talk a lot about right now, though they actually also asked the users whether they had seen the news before, whether they believe they had seen the news before. Okay, so for every news, we have the credibility rating, but we also have a yes/no variable that tells us whether the user thought he had seen that news before. Okay, now all these variables here are experimental manipulations. They are individual differences, and they can all affect the bias. They can all lead to the bias to be shifted in one or the other direction. Let's take the scene manipulation. If I say that I saw that news, well, if I believe I saw that news, I should say yes, right? So that should clearly shift my criterion to the right, to the left, but I mean, it gives me more, so I have a much higher probability of saying yes if I see that. And so in the analysis, when we then use the cumulative link mix model to estimate these parameters and to estimate the experimental and the covariate effects, these variables will all have a potential to be significant in affecting the criterion. And not only the main effects, but also, of course, whatever interactions you include for them. And at the same time, in the same model, we can also get estimates on D prime. And in the model, basically all the terms that I have up here and that basically code whether there will be an effect on the criterion will interact with the truth status. And the truth main effect is an estimate of the overall D prime. And the interaction of truth with all of them up here is then basically the specific effect of that manipulation on the D prime. How much does that manipulation change the D prime? Everybody still with me? Yeah, okay. And of course, we have 6 ratings, so we can estimate 5 response thresholds. You know, basically we don't have only one criterion, you know, we have basically 5 locations of the criterion. And now the final part of that one, and then you pretty much have the, you know, the big picture here. Traditional signal detection experiments were carried out in single case studies. And then the idea was, those were psychophysics experiments. And the idea was, you know, they have that saying that psychophysics never showed anything except that you can't bore a German. I think William James actually said that. Basically, you need subjects to sit there and listen to signals and noise for hours and hours to get enough data on a single subject to really estimate those parameters reliably. And we can't do that, you know, like we have like 7,500 subjects, and they are not Germans. They are web experiment users. They are Facebook and vKontakte users. And so they only rate 8 items, 8. That's incredible. And the 8 items come from a 2x2x2 design. You know, half of them are true and false, half of them are from the dominant and from the alternatives perspective, and another one was a kind of a source manipulation, which I glance over right now. So we really don't have much information from a single subject, but we have lots of them. And I was really surprised. That really blew my mind. That, I mean, of course, you know, so you can't really estimate a hit rate and a false alarm rate based on 4 items. It just doesn't make much sense. So you can get those estimates really only by aggregating across subjects. And of course, aggregating across items. And that's where the linear mixed model, or in this case, the cumulative linked mixed model comes in. You know, so we treat subject as a random factor. And we have about 1,500 for each of 5 data sets. And each subject rates 8 items. But this is our random factor subject. And item is another random factor. So Victoria Vizyajeva wrote those. The true news were actually found in the wild. They were found via topic modeling. So there was very sophisticated technology in place in identifying the topics of the true news and selecting the true news. And then using that as a backdrop, Victoria pretty much wrote fake news corresponding to these topics. And that was really ingenious, okay? But we of course need more items to not just study a single item effect. And so basically we had a total of 24 items, well, a total actually of 96 items. So it's 3 times, I'm getting screwed up here now. Let me just make that sure again. No, there were basically, right, okay. There were 24 items about Russia. And there were 24 items about the Ukraine. And there were 24 items about Kazakhstan. No, I'm getting lost here now. I must have.
I can help you there if you want.
Can you quickly say it to me?
Yeah, so 24 items about Kazakhstan, 24 about Ukraine that were shown to Russian users. Then Kazakhstani users were shown 24 news about Russia, and Ukrainian users were shown other 24 news about Russia that didn't intersect with those that were shown to Kazakhstani users.
Okay. So but basically when we now have the, so I'm now focusing basically on a subset of the data. And that subset of the data is, as Olesya just said, are basically the Russian users who were shown news, international news about Kazakhstan, okay? And I'm also including Kazakhstani users who were shown news about Russia. So all the users only saw news about a foreign country, which reduces, of course, the familiarity with the news and makes it more difficult for them to discriminate it, okay? Now, remember that basically each user only saw 8 news, okay? But sort of the news they saw were sampled from that pool of items that I just described, and then which in this case would be a total of 48 items, 24 about Russia and 24 about Kazakhstan. Everybody cool with that? And so if I now basically look at this subset of the data, yeah, there's a question, Ralph.
Yeah, thank you very much. Just to clarify, is this what is called the alternate and the dominant perspective?
No, that was alternate dominant is within, is a manipulation within, okay? So, so this was the manipulation. The manipulation I just described was basically the manipulation between countries, if you want, okay? So I'm comparing, and there's sort of some argument basically that Russia is more autocratic than Kazakhstan. Both are autocratic, have autocratic governments, but that basically there's a little bit more, and that should translate into a different effect that we'll talk about a little bit later. Okay, so that was that one. And crossed with that one is basically the alternative versus dominant view, okay? Because every subject rated 4 dominant and 4 alternative news about the other country. All right?
Got it. Thank you. Yeah.
Okay. So what you see here now is basically already the estimate that comes out of the model. Okay, so we basically take those data, and I'll show you a little bit later. I'm not going too much into the detail, but I will give you a little bit an idea how that is actually done. So this is not a graph that I just sort of drew up. These are really the data that come out of that experiment if I compare the Kazakhstan and the Russian samples. And so you sort of see we have a total of 3,038 subjects. We have a total of 48 subjects. And because every subject rated 8 items, we have a total of 24,304 observations. And if I now analyze those rating data the way I described it, I basically end up with a D prime. Okay, obviously the true news distribution sits to the right of the fake news distribution. And these are sort of the thresholds, the response thresholds that were estimated as part of that whole procedure using the whole data set. Okay. And now, of course, if you want, this is in a way the baseline, right? We have a D prime, and we now have our 5 criterion locations. And now we can sort of see, well, how does a specific experimental manipulation or covariate affect the D prime, and how does it affect the criterion location? And what I'm going to show you is the interaction of scene and country. Okay, so, and this is, I picked it because for me it's in a way a treatment check, really. So if a subject rates an item as seen, they really should say yes. I mean, that doesn't make sense to sort of say that I've seen that item and then basically, you know, because fake news, they couldn't have seen a fake news. So if they believe they saw it, it must be a true news. There's a little bit of a qualification on it, but we can talk about it. You know, you can still think that you saw it, you saw a fake news, but I think that is that is not such a likely event. It's a little bit more difficult with respect to whether that also affects the D prime, because you know, having seen something doesn't necessarily mean that you only saw the things that were true. You could sort of look at a fake news item and still think that you saw it, but you confused it with something, because Victoria wrote her stories so clever that they really look like true news. Okay, so it's not, so basically believing that you saw the news doesn't really mean that you are right about it, you know, that you saw it. You could be wrong about it. You actually think you saw a fake news. And so if we look at these data, and this is now also coming out of the data from that experiment, you sort of see that basically the comparison. Let's first look at the Russian users. Okay, you can sort of see that for the not seen, the items they did not see, the criterion are way to the right of when they said that they'd seen it, right? So we sort of see that the criteria are shifted towards the left for the items that the subjects rated as seen. And that means they are much more like, obviously, you know, if your criterion sits over there, you have much less evidence to say, yes, I saw it. But there's not much of a difference in the D prime. Actually, you can sort of see that for the Russian users, the D prime, it was actually somewhat larger for the items they claimed that they didn't see versus for the items they claimed they see. Just a second, Alma, let me just finish that one. And then if we look at the same thing here for the Kazakhstani users who saw the news about Russia, again, we see sort of that gigantic effect of the seen, if they rate an item as seen. And actually, in this case now for them, the D prime is somewhat larger for the items they rated as seen than the items they rated as not seen. Alma.
Yeah, thanks. I kind of thinking of what you said about if they saw a piece of news that they should actually rate it as real news and not fake news. Doesn't it mean that this in some sort is actually measuring their memory, their
Yeah.
recall.
Yeah. So in a way, if they have a memory, you know, I mean, right. So this is getting into some of the technical things. So you are right, you know, so in a way, there are two things running around here that we have to keep in mind. Victoria wrote news about the Ukraine and about Kazakhstan and about Russia, fake news. Now, of course, we cannot really expect her to write the news of the same difficulty, you know, that all her news are basically equally difficult to discriminate from the true news of that country. So there's always sort of that issue of the material effect when we look at that factor. But of course, there are some interactions where that doesn't really make much of a difference.
Yeah, I definitely get.
I'm sorry.
Sorry, just before I totally get that. I just think that, I mean, if I think that there is, like, you could be exposed to a piece of news that you don't think that it's you don't think that it actually is a true depiction of the world. So this is fake in that sense.
Basically, you're anticipating my discussion slides. Is
okay,
that okay?
Okay. Yeah. Sorry.
Back a little bit. Yeah. Okay.
Yes.
Steve.
Yeah, just quickly. I mean, to me, this seems like sort of an illusory truth effect, where anything you've seen previously you think is true,
exactly,
because the criterion shifts down. So
right,
you're more likely to say, yeah, that's true,
right,
based on your subjective sense of having seen it, right? Because the seen and unseen is not objective. That's also a response.
Exactly.
Okay. Yeah.
And I really use it mostly as a control variable, but it sort of turned out that it was really like the biggest effect I had. And so it's a nice covariate. It's not a manipulation. It's a covariate that I can include just like other people include age and stuff like that, right? And sex. So it's not an experimental manipulation. Absolutely. Okay. So this is a rather busy figure, right? And I really like it, and I sort of started out with this because I really want you to keep, to have a little bit of develop a memory about that basic theory. This is in a way how the data translate into the theory, right? But of course, we can simplify that a little bit, and the simplification is actually the presentation of the same results is via receiver operating characteristics. And this is shown here. So these are actually the same data. But here now, we basically, again, you sort of see here and actually you should look only at the first row for now. Okay, so these are basically the model. The M stands for model. Okay, so this is basically what the model predicts, what we get from the data when we ask the model to give us predictions about this huge set of data. And basically what it shows you is the receiver operating characteristic plots the C-score of the hit rate over the C-score of the false alarm rate for the 5 thresholds, and of course, broken down by whatever combinations you have. And so what you see here is, first, you see the big shift of the criterion. You see in the fact that the yes response is shifted upward. Okay, so you have a much larger tendency to say yes whenever you look at a blue curve, and that is just what we've seen before with the shift of the criteria toward the locations to the left. Okay, trust me, it's also it's whether you multiply it by -1. So here it's in a way the higher up, the more yes you say, the more inclined you say to yes, and at the same time you sort of see that there is not much of a difference between the blue and the red line, which are actually parallel. And this is the other thing that blew my mind, I must tell you, that these receiver operating characteristics are the fundamental test of whether the assumption of equal variance of these two normal distributions is met. If the two normal distributions for subjective evidence of fake news and the normal distribution of subjective evidence for true news are normally distributed, as I say, and if they have the same variance, then this line has to be parallel to the diagonal. And in traditional memory research, that you don't really get that very often. Typically, the line is somewhat sloped in it. And the slope of the line would indicate the difference in variance. So it can be either this way or that way, depending on which of the two distributions has more variance. So it is absolutely stunning that these rating data are in perfect agreement with the fundamental assumption of signal detection theory that there are two subjective distributions of evidence. There are two distributions of subjective evidence, and that they have the same variance. So this rules out other models like high threshold models, or trivially the model about unequal variances possibly, which wasn't too. And at the same time, you sort of get the results basically that relate to the criterion stuff. And the slope here varies between 0.98 and 1.02. And ideally, you would need a slope of 1. And now these are model estimates. In the lower panel, in the lower two panels, I show them to you if I just compute them as empirical estimates. So no linear mixed model, no cumulative mixed model. All I'm doing is I'm computing the hit rate and the false alarm rate, C-transform them, and plot them. And so you can sort of see that the model cleans up a little bit, but the basic empirical data themselves, so without any estimation, you also have already support for that stuff. So this is really gigantic. And let me just show you, I jump ahead here. So I've shown you basically the left two panels. So this is what I just showed you, broken down with some other conditions. And these are the three other data sets we have. So these are 5 independent data sets, each of them based on around, so here you sort of see the number of subjects. So 1,500, close to 1,700, close to 1,500, around 1,500. Okay, independent users. I think this is really incredible. And okay, so now I will postpone. So I have a few slides that show how we do that in R. Okay, so this is all the estimations are R-based, but I just sort of present them as teasers because this will require a little bit of presentation and talking about it, but it's not really different if you have run a linear mixed model or generalized linear mixed model. We use a probit link instead of a logit link and stuff like that, but it's basically the same machinery underlying it. Now, what the models allow us is, of course, now, and this is sort of where the mixed models addition comes to it. And the mixed models addition means that we can actually estimate for subjects the variance on the criterion. This is this, okay? So subjects differ in their location, in their overall location of the criterion. So there are some subjects who are more yes sayers and some subjects who are more no sayers. And the variance around the population mean is captured in this parameter that's here listed under standard deviation. We can also estimate for the subjects the variance, the individual differences in D prime. So there are some subjects who have better discrimination than other subjects. And the variance around that overall D prime is captured in this parameter 0.1402. And finally, we can also estimate, in this case, the individual differences in the size of the C effect. Okay, so for every subject, we compute for the criterion location, how much effect does, if a subject says, I saw that item, how much does that change that subject's criterion in the right direction, towards being in the left direction, towards being more of a yes sayer then. And so this is this variance, which is very large. And now actually, we can also estimate correlations between them. And that means for the subject, we can actually correlate the criterion and the D prime. Okay, so this means that in this case, subjects who actually were better at discriminating true and fake news actually also had a stronger tendency to say yes. And this is, for example, then, of course, how does it correlate with the C effect? So this is, again, if you are familiar with mixed models, these are the correlation parameters. Now, remember that I told you that within a subject, the criterion and the D prime are orthogonal. So at that level, they are mathematically independent. But then when we move up from the lower level to the aggregate level, we, of course, can find correlations between them. This is just so cool. I mean, this is just so cool to start out with a zero correlation and then sort of move up a level, and all of a sudden the things pop out. Okay, and I just can show you. So basically, I give you, how do we test whether this stuff is significant? And this is the old ANOVA stuff, and this is like the 3 models I compared. So in the first model, I had no correlation parameters. Then I had basically only the criterion and the D prime, and the 13 is the one that you see here. And you can sort of see that basically the likelihood ratio goes up, the AIC goes up, and even the I didn't notice that it doesn't give the BIC, but basically, the correlation parameters are significant. Steve?
Yeah, super cool result. Just commenting on the correlation between criterion and D prime. I mean, the way, when I look at this, my first thought would be, okay, so people place the criterion optimally because they know, they try to find the sort of sweet spot in the middle to maximize the trade-off between, the optimal decision point, which is intersecting the two distributions. Is that what might be causing these correlations?
So I would really say that, so actually we could look at it later at the 12 where I didn't have the C in there, then that correlation turns negative. So correlation parameters in general, I think the first time you compute them, your intuitions are only a heuristic. And basically correlation parameters really are only a heuristic piece of information that can guide you in the next study. Now we have the nice thing, because we have 5 independent samples, if you want, we can sort of see whether that correlation comes out the same way every time, or whether it has to do something with the C effect. So I had expected a negative correlation. I thought, the better they are, the less they will be yes sayers, but this is very difficult to judge because there are so many factors that are statistically controlled. So I'm running a little later. Let me just try to get through so that we have a little bit of time also to talk about. Is that okay, Steve? I mean,
yeah, of course.
But basically, this is really, I did the correlations for the first time this morning, so I haven't really thought about them much myself. I should say that too. Yeah, so I wanted to give you one more result, which highlights another important part of where I sort of think the power of that approach comes from. And that relates actually to the 2, theoretically, in my opinion, most interesting variables we had in that study. And one is, of course, the narrative, and the other is the government support. So we have an experimental manipulation, and we have an individual difference manipulation. Okay, and now we sort of basically check, well, how does that also interact, and does that also interact with country of the user? And this is the result. So here I need to switch to a slightly different format because we still need to find a way of how we visualize covariates rather than factors, right? But the top part is the criterion, okay? So this is basically the estimate of the criterion. And what you can sort of see is that when we look at the Russian users, that for the dominant news, there is an increase in the criterion, a tendency to say yes, to accept the news as true, as the government support of the user increases, okay? So the more a user is in support of their government, the more does the judgment of dominant news induce a tendency to say yes. So you could call that a confirmation bias, because dominant means being written from the government perspective. This effect is not at all visible. Maybe it's even going slightly in the opposite direction with government reading alternative news. And you can sort of see that basically this effect is much more pronounced and extends across pretty much the whole range of government support compared to Kazakhstan, where in the Kazakhstani users, sort of the lower users' support of government does not really show that differentiation. And only sort of when a user becomes very supportive of their government, then all of a sudden this trend that we see here for the Russian users also starts to emerge. Okay, so this is basically now the result at the level of the criterion in the signal detection theory. Now, how does that compare to the figure that we published or try to publish in our big paper, where we analyzed the credibility ratings? Here is figure 2A from that paper. Now, this is so cool again, right? So what it shows you is basically that the credibility rating reflects the bias. But if you only analyze the credibility ratings, what you miss out are, of course, effects that potentially are related to the discriminability of the news, because they are sort of merged in, they are sort of mixed into these effects here. And I just want to show that basically, these kinds, so this is like, this is of course an interaction between support, narrative, and country, but actually we only the three-factor interaction was not significant. What is significant is narrative by support. Well, that's pretty clear for the criterion here. So obviously, narrative by support means you can average the top two panels, and for dominant it goes up, and for alternative it stays flat. Then on the D prime, we actually have two interactions. One relates to narrative by support and one to narrative by country. I'm not going into the details now. They are a little bit more difficult to interpret. There could be effects related to the difficulty of the material of the items for Kazakhstan and the items for Russia. But what I'm saying is basically every figure of that sort has a correspondence in a fixed effect estimate in the cumulative linked mixed model. So now maybe just briefly on the discussion. So we know that reading fake and true news is not a signal detection experiment in the old-fashioned way, where we could really rely on subjects being honest. We know now that basically we have the situation that when it comes to fake news, ideology and whatever have you may cause to consciously lie. They know it. And there's a very interesting idea. There's actually a paper out on introducing signal detection theory, and they listed that as a caveat. They sort of said, well, look, when we go to analyze these kinds of data, then we really run a little bit the risk of overlooking that people are much more likely to not tell us the truth when we ask them to rate news. And you all know the Obama-Trump inauguration slides, where sort of depending on if you are a highly educated Republican, you just simply say that there are more people on the Trump inauguration slide than on the Obama inauguration slide. So how would this effect translate into that signal detection approach. And my argument is it will lead to a negative D prime. Okay, and the reason is basically, think about it, you run the experiment and by accident, you wrongly allocate the yes and the no response. Okay, then of course, basically, after you find out when the data are collected, you can still analyze the data. You just have to recode the yes/no response for that subject, and you get your nice D prime. But if you don't record it, of course, then the true news distribution is in a way, you basically have the situation that I depicted here. You basically say yes, and so now all of a sudden the fake news proportion of the false alarm rate is larger than the hit rate. And when the false alarm rate is larger than the hit rate, you get a negative D prime. So this is, in a way of getting at the issue of lying, to put it simply, or consciously giving a false response. What are situations like that? Well, I mean, so it's not a nice example, it's a pretty ugly example, but I think it drives home the point. If I'm surrounded by a bunch of neo-Nazis and they ask me a question, I will tell them what they want to hear, not what I think, depends on if I can run fast enough. That would be another option. But so in a way, there are situations where we, I think, justifiably just say something to get out of it, right? And so in a way, what I'm saying is there are situations we may be able to experimentally engineer where actually the D prime could become informative about that part of that whole theoretical issue point. Okay, and it's just important to realize that this is not a bias, right? The bias is completely independent of the negative D prime. So the bias can have, again, be way up there or way down. So it is a genuine new type. I mean, and traditionally would have probably also subsumed that under the label of bias. Now, I talked to that actually with Edgar and Lena, I think, and of course also in the group. And people always say, but this is not all. So I had really high hopes. But then there are other ways how we can get at a negative D prime. And I think the nicest way was in an email by Olesya that she sent me when we argued about that. And she says, well, it could happen, for example, because Victoria made all the fake stimuli look very true-like and all the stimuli look very fake-like. And that's true. And actually, we are in a situation that we can actually look at that already, because we have a very small D prime. Our D primes are like 0.30 or something like that, or between 0.20 and 0.30. Typically in signal detection experiments, the D prime is more like 1.5 to 2.5. So we have about a factor of 20 smaller D prime. Now, if the two distributions are so close, then you can sort of assume that, if I pull them out, that there is basically a fake-like true news distribution and a true-like fake news distribution. And if I just pull out those items and run my signal detection analysis on those two subsets of items, then I will get a negative D prime. So again, I think it's something that is important to know, and it's something that we may actually want to implement in experiments to actually sort of see whether we can, with certain constructions of material, if we include certain features in the items, whether that makes a true item look like a fake item or vice versa, right? And then again, basically this manipulation, if it is successful, it should in a way show up as a negative D prime relative to the standard one. And my final slide here. Yeah. So I think basically what I tried to show you is that with the signal detection approach, we can achieve a separation between the discriminability of fake and true news and the bias. And this is, in my opinion, absolutely fundamental. I think if the term bias hadn't already been used by signal detection for a long time, I would have said, they took it from fake news research, right? I mean, it's really the yes tendency, the no tendency. There's just such a conceptual map between the concept of bias in signal detection theory and the one that we observe when we talk about rating news media. It's much more sophisticated. I'm learning day by day, but as a first approach, I think it's not bad. So where can we take it else? Well, we can try to identify the features, the conditions that make fake news read like true news and vice versa. And we can, of course, also look at individual differences and item differences in experimental effects on discriminability and bias. And then we can sort of start, and that's what really brought me into that field. I want to separate the users who are wedded to an ideology, cult, sect, true believers of fake news, rejectors of true news. And if I find, so this is my first methodological attempt to get at that issue, because I think that's absolutely critical for us to save democracy. And the same thing holds here. And I should stop with saving democracy. Thank you very much for listening, and thank you for my collaborators. And I'm very much in love with this project, obviously.
Thanks, Reinhold. That was terrific. We're technically at the top of the hour, but that doesn't mean we necessarily have to stop. I do have a new meeting coming up, but not quite yet. So I'm more than happy to continue discussion and open the floor to anybody who wants to ask a question. Raise your hand, because there's so many of us. It's hard to know who wants to talk without raising a hand. Yeah, Ralph.
Yeah, thank you very much. I really enjoyed the talk. I was wondering whether signal detection theory can also be used to study the sharing behavior of individuals, or whether there's actually a nonsensical concept to think about.
What do you mean with sharing?
Well,
whether users promote the forward stuff and like that?
Yeah, exactly. So next to accuracy, we know that, of course, like what you share and not share is extremely important, and only so much influenced by the actual accuracy that you perceive. So can you see applications of signal detection theory to understand better also sharing behavior, or do you say, well, there's actually, it doesn't make sense to think about the amount of evidence for sharing versus non-sharing?
So I have not thought about it, but just one quick response. I mean, I just last week, actually, for the first time, I read those papers by Van Bavel, and I think they sort of try to really argue that the sharing behavior is a very good, valid indicator. Even if people just say, would you share it, that has a high ecological validity to what people are really doing. And so in that sense, it definitely is a variable that I had planned. I have it already on my list. Actually, my colleagues in St. Petersburg will tell you that I already sent an email. Can we include that question in our next experiments? So we definitely can include it as a covariate, right? I mean, there's absolutely no problem with a covariate, whether you can move it up into the dependent variable state. That I need to think more about.
Yep, thank you.
But I would assume that it has, if you share it, that's something that you are committed to, right? And so that should really go with the criterion, I think, in many ways.
Yeah, exactly. But I would be also very interested in if you can actually use signal detection directly to predict what is more likely to become shared, right? To being shared.
But okay, so you definitely, signal detection theory has the one thing, you need to have a distinction between true and false, signal and noise, A and B, okay? So as soon as you can objectively map your stimulus, your experiment, so if you think of an experiment where basically the shareable thing becomes something where you can make a true, not true distinction, then you are in business, I think, So you always have to be able to, it's really very simple. You have to be able to compute a hit rate and a false alarm rate. When you can do that, you can go into the signal detection line.
Yep. Thank you.
Okay, Alan.
Yeah, if there's still time for a question, I would like to ask this one. So for me, a different criterion can arise from different underlying cognitive, or if you will, different cognitive processes. One is because you assume there are different base rates. So true is, for example, much more likely, different error costs, or different stimuli categorization or evaluation. So while you're reading it, you have a biased evaluation of the stimuli itself. So what do you think is driving actually this criterion
Okay, excellent question. And I forgot to mention that, and I'm very happy that you asked it. Okay, so we are using what's called the CLMM2 program in the ordinal package. And the CLMM2 program has the advantage that we can use multiple random factors. So we can have both subject and item as a random factor. What it does not allow is that we can sort of, what comes with it as a constraint is that, as you can sort of see when you look at these red lines, that the pattern of red lines, the distances between the red lines is basically the same, okay? So we cannot basically, we can of course estimate effects, but it's always the ensemble of the thresholds is in a way a constant. Now, when you, and I think that gets at your question, if unless I only heard what I wanted to hear, but you know, basically, if you assume that that the experimental manipulation has that you have different criteria for different type of conditions, then of course part of it is captured in the fixed effect, right? If you can do that, but of course you could also assume that there are different patterns of how basically the criterion locations map onto the response thresholds. That could be different. And when you use the precursor of the CLMM2 program, which is I think called CLMM, there you can only use one random factor, but it allows you to estimate that more precisely. Max, maybe you want to add a sentence on that, huh? Maximilian Rabe knows that stuff much better than me. Or did I explain it?
I don't think I have a lot to add to that. Yeah, just that the names of the functions are the other way around, I think. But yeah, there are a few constraints on modeling the placement of the individual criteria. But yeah, I think you would be more flexible if you like move to BRMS if you do Bayesian model fitting, but yeah, if you're sticking with the ordinal package, that's that's pretty much it. Yeah, but it's still
people should first understand the frequentist approach, and then they can move to Bayesian, I think.
Well, I think Bayesian is cool. I'm a huge BRMS fan, so.
Okay, no problem.
I think this is, Reinhold, this is going to be a religious debate. So
no, and I was just kidding. Let me, you know, it's just because I don't understand it. Olesya has a question, I think.
Yeah, you can comment. I want to say that I'm really fascinated to have Reinhold on our team, and I think we're just super lucky to have met him. But at the same time, I'm a person who always keep doubting and challenging this SDT theory, which is very new for me, and so I have a lot of like misunderstandings. Probably everybody in this room understands what I'm wondering now. So in a simple acoustic experiment, I can understand why we think that subjective evidence is continuous, because we can create a continuous change of a stimulus. So from perfect signal to perfect noise and everything in between, it's continuous. And therefore, it is logical to assume that subjective evidence is also a continuous variable. Probably physicists have some ways to test it experimentally, but I'm really not sure why we are looking at a bunch of text as a continuous signal, continuous stimulus to produce a continuous evidence.
Olesya, you never use that example, but that example is perfect. You know, when you go back to the original signal detection approach, they didn't manipulate the stimulus intensity. They always presented the same stimulus. It was only one stimulus. And the distribution, the subjective evidence of having heard the stimulus or not having heard the stimulus, for the noise at the same time, that is basically generated due to the internal noise of our system. Okay, so in a way, if you want, the traditional approach that you just described was actually that you don't manipulate the stimulus intensity. because you assume that the stimulus intensity over repeating the same stimulus over and over will generate a subjective evidence distributions. So the same stimulus will give you, sometimes you think you have more evidence, sometimes you have less evidence, right? And so in that sense, and since that's where basically signal detection comes in, it doesn't matter whether you work with one, but, well, I shouldn't say it doesn't matter. It makes, of course, you know, it's much cleaner if you can have the same stimulus. So we are a priori dealing with much more noise than the original people worked with. But mathematically, it's no different. You know, you have your distributions, and then it's an issue of statistical power, whether in a way you can detect the signal in the noise, basically. Do you see that difference? Yeah.
Yeah.
Okay.
Yeah. Thank you. Thanks a lot.
Okay, folks, it's 1:15. I'm going to have to go very soon, so I'm tempted to wrap it up, but there's also 37 people still here. If you want to keep going, and by all means, Almog, are you willing to continue hosting? I don't want to cut the discussion short. It's just I have 2 minutes to be somewhere else.
Yeah, no worries. If there's still questions, I'm happy to keep moderating.
Okay, great. So, but I want to thank Reinhold on my way out. That was great. Thanks so much for doing that. Really appreciate it. And yes, if there are questions, please raise your hand. I can still hang around for 1 minute before I just disappear.
Looks like everybody's overwhelmed.
I think you just said it yourself, that we need some kind of binary distinction between the true and false in order to apply signal detection theory. But what if in reality there is more of a continuum between true and false information out there? So then signal detection theory wouldn't apply work anymore for modeling that, right? Or do you see any chance to also capture that?
I mean, you can always post hoc categorize, right? So, but then this is not nice, right? I mean, you can. So I'm really somebody who has tattooed on his back, don't binary a continuous covariate, or but. Yeah, I mean, that is one. I mean, so you need the truth status, right? Because we have. I think maybe Edgar knows. Edgar Erdfelde is here also. He's also very knowledgeable, and some of those aspects probably knows more than me. I think there are some ideas of having multiple, to work with more than two distributions. So there are in a way generalizations of signal detection theory. In that sense, maybe. But I really, I must say, I'm not at all familiar with it. Edgar, do you know about those multidimensional signal detection theory stuff? Is that something that is pursued actively, or?
Definitely, it exists. I don't see how it can be applied in this context. So actually, I find your approach very convincing. The more so since you make the point that you can equate variances, which I didn't expect at all. This is very unusual, as you mentioned in the memory literature, for example, you don't find equal variances typically. So given these constraints, given the paradigm, I find it very plausible to model it in the way you did.
Okay. Let me just add here on, I see Bashir is here as well, just one sentence here quickly. Why? So I think that the fact that the assumption is met, the equal variance assumption, it's not a necessary, so I think it could have come out different. But I think the fact that we have such small d prime values really basically made the items marginally discriminable for subjects. And so in a way at that level, so I'm sort of wondering, so basically the smaller the d prime, the more likely, I guess, it is that the equal variance assumption is met. I think that basically as you move up into d primes of 1.5 or 2.5, then all of a sudden the classes become much more distinct. And then, of course, sort of the idiosyncrasies of the distributions may play out much more strongly. And then you can sort of are more likely to see those things. But as long as we work at, and in this field, this is another thought, I've almost say when I give this talk, it's funny that traditionally signal detection theory was out to correct for the bias. The goal was to find sensitivity, to get an unbiased measure. That was the idea, to get an unbiased measure of sensitivity. Now, when we move into the fake news domain, what we actually want is we want to get an unbiased measure by an unbiased measure of bias. That is, we want to sort of remove whatever differences there are due to knowledge between the subjects, due to stimulus conditions, to in a way clean out the effect of our experimental manipulations on the bias, right? So in a way, the approach that we are sort of advocating here really also in a way puts signal detection from its head on its feet, or the other way around, whatever your perspective on it is. It's but of course, mathematically, it's the same, right? We estimate everything at the same time, but conceptually, the way you frame it and the way you may think about your experimental manipulations, we should be much more creative about how we can implement confirmation bias and stuff like that. And live with the fact that we will, it will be difficult to write material that is equally discriminable across between item conditions, basically. Yeah. Okay, Mubashir.
Hello, thanks for a lovely talk. That was also very passionately delivered. It's very inspiring. In your talk, you mentioned how like signal detection theory is a good fit for studying sort of false news and specifically this sort of experimental paradigm. And this kind of goes against the talk, but I'm wondering if you had thought about other modeling frameworks or other frameworks that would also be suitable for studying this kind of experimental setup or this question, for example. So that's the question I have.
Yeah. So I'm a very much a theory-driven person. Okay, I just don't like research that. I mean, I shouldn't say that. I don't like it for myself. Everybody can become happy however they want. But for me, anyway, it's always important that I come from a theoretical perspective. And I think the more you are into multivariate statistics, into complex statistical models, the more you will appreciate having a theory that guides you. And so when we started out like that, the alternative approaches I thought of were, of course, the ones that are typically contrasted with signal detection theory, like looking at high threshold memory theory or looking at unequal variance assumptions. Now, in a way, I premeditated all that stuff, but as soon as I had the ROCs I showed you, I decided, okay, for now, I really don't need anything else. I mean, it's quite clear that high threshold theory cannot accommodate these data. And so everybody who just analyzes accuracy with some sort of correction for guessing is not correctly, is not using a model. So the high threshold model maps onto a correction for guessing type statistic, right? So that's frequently used. But if you have these kinds of data, it's quite clear that the high threshold model is absolutely out, right? And so in that sense, I didn't get very far with my alternative approaches, but yeah. I'm also happy if one of them works for now. It will, the sadness will come soon enough, I think.
We have a question in the chat.
Oh, maybe can you read it to me because I don't see the chat.
Maybe Maximilian would like to.
It's not a question. I was just adding to something to Philip's question from before. Yeah. I think the question was whether you could use a continuous status or truth variable. And I think if you use the regression approach to signal detection theory, that should work as long as you have a reason to assume that the continuous status or truth linearly maps onto the distance between the noise and target distributions, then that should work. Yeah. And you don't have to dichotomize the that variable.
Great. We'll do that too then.
That's, by the way, something you cannot do with the conventional approach to signal detection theory. So that it's only possible in the regression approach. So.
Okay, do we have more questions? All right, then Reinhold, thank you so much.
I enjoyed myself. Thank you, guys. It was really great. I also like that international flair that we have here today, right? I mean, if the world goes down, we should really counteract at all levels. I think that is just our task as scientists. You know, we are the ones, we know better, and we should really feel confident that we know better. Okay, guys, see you all. Thank you very much.
Bye all.
Thank you, everyone.
Thank you very much.